shaky for us.
Good afternoon, everyone. So it is really a pleasure to have Dr. Sujoy here as the speaker in our department, and Sujoy has been our student in the SMOS Center, and he is Professor Ravindranath, and he has also been my friend, my collaborator. And after doing his PhD, he did his postdoctoral fellow from Japan, and then he also did his postdoc from Colima also, right? From Mexico. And now he's presently a faculty member in the university in Mexico, in Colima, and his research interests are in gravity and quantum field theory, as you can find now. And today he shall be speaking on revisiting the enigmatic early universe with T vacuum state. So,
Thank you very much.
Right down to
Thank you for coming to the seminar after lunch. I think all of us like have sleepy. Let's see if we can continue and we can understand each other fairly well, communicate each other fairly well. So first of all, I want to thank my supervisor, Professor Banerjee, for hosting me here again, and Sunanda for facilitating everything in SMOS, providing accommodation and all that. Thank you very much. As Sunanda said, I was a PhD student here once. I completed in 2012, 11 years ago. Then I have been traveling around. In these 11 years, in 1.5 years, I was in Ayuka with Professor. Then rest of the time, another 2 years in Japan, mostly 7-8 years in Mexico. So I'm going to speak in Spanish. This work is basically after my PhD, but I have not written a lot of papers in this subject, but I have been kind of consistently staring at it and see what I can do, and now I have some agenda to work on. If you guys are interested, you can see these papers, and if you are interested, anytime you can write to me. You are interested for discussions. These works started. This work started in 2013 when I was in Paddy as a postdoc, and then it kind of continued, not exactly in this our universe, but in the lack of information problem. In my second postdoc with Professor Daniel Sudaski, although I have not written with Sudaski in this topic, but I have written in related topics. So I learned from him a lot. So once I went to Colima as a faculty, then I had more time to think about these issues that I didn't have enough time in postdoc. And these are the work that I did after going there. Can I change it with something? Okay. So I would like to thank my collaborators, of course, Professor Padmanabhan, you know more, Daniel Sudaski, Juan Salazar, Damar, Carlos, these are my students. So when we think about our universe, one thing that comes to our mind is this beautiful picture, which is the CMB background, as we see by the plant satellite. Before that, there was scope, WMAP, and all that. Using the finest resolution that you have. Basically, this says that the early universe was fairly isotropic and homogeneous, but there is some change in the color coding. This change in color coding belongs, like, if you are red, that means the temperature is slightly lower, and if you are blue, temperature is slightly higher. So there is a little bit of temperature. Well, there is fluctuation in the temperature. If you see the CMB, Let me remind you where exactly is CMB is. You have this big bang, and then after that we have this inflationary period. Of course, it is not exactly proven that we had inflation, but it is a well hypothesized theory. And after that inflation, we had radiation-dominated universe. The inflaton field decays into radiation, and the universe started getting cold. And at some point, at the end of the radiation-dominated universe, when the matter, well, from the plasma state, when we started building, hydrogen, so nucleus, formation of nucleus and atoms and all that, what happened is that the photon becomes decoupled and it started traveling. So in the beginning of matter or at the end of the radiation dominated universe, we see this CMB that I showed you. Basically, free photons coming after the after the formation of matter and all that. So these photons travel to us and we see them. So what happened that at this point of time, for 2075 years, the temperature was 2700 Kelvin, but because of the gravitation of because of the expansion of the universe by a factor of z equal to 1000, we see these photons more or less about 2.7 Kelvin, fairly isotropic. So what is usually believed is that after the Big Bang, the universe went into rapid expansion, most likely started from inflation, and then it went to radiation dominated and matter dominated and to dark energy. The earliest observation that we have is, of course, the CMB when the universe was more or less this age. CMB is remarkably uniform, almost black body radiation, about 2.7 Kelvin temperature, but it has tiny fluctuation as we see of the temperature, and also there is a departure of Gaussian area. There are non-Gaussian involved. Each of these fluctuations and departure from Gaussian have tremendous interpretation and they have crucial clues for understanding our daily universe. So I'm not going into detail how the non-Gaussian tells us about the matter content or how. I'll be more focused on these tiny fluctuations, these temperature fluctuations. So the interpretation of the tiny fluctuations in the CMB temperature is as follows. These tiny hot and cold spots that we see in the CMB are caused by initial density perturbations. The density that means these places where we have the different color coding. Some of them are highly dense, and some of them have a low density, so that the denser region has more temperature, and the less denser region has less temperature. So this the interpretation of that tiny fluctuation is that we have tiny hot and cold spots in the CMB are caused by initial density perturbation. Now, the way we understand this is as follows. We have the temperature fluctuation in CMB, and we say this is equivalent or this is interpreted as the primordial density perturbations in the universe. And then we also understand that these density perturbations are actually the seeds of structure formation. So these are density perturbations, which are classical, of course. Those density, the smaller regions and small dense or higher dense regions, after the expansion of the universe, give rise to structure of the matter. And then it was like a gaseous state, and then gravity kind of pulled together the regions which are nearby were pulled together by gravity, and that after expansion gave rise to the structure like the first star or these things. So at this point, when we are talking about early universe, those are only seeds of structure formation. Structure formation will happen for next million years, but those are the seeds where we have, these are the seeds which later expanded, give galaxies and galaxies. So here, this identification of the temperature fluctuation or primordial, this equivalence is empirically hugely successful. what do I mean by empirically successful is that here, when you have temperature fluctuation in the CMB, you are an astronomer. Basically, you astronomers detect photons and distribute them with the direction they come, then the frequency of the photons and temperature, etc. So as an astronomer, you just do this distribution of these photons that they come from different directions and see how they change with angle and what is the temperature and all that. So it's basically your detection and you use classical physics. There is nothing, it's just the distribution. Once you think about this part, which is the primordial density perturbation, the reason I say it is empirical, because as an empirical physicist, what we do is that we use a stochastic near Gaussian classical field distribution to model the temperature fluctuation. So you see the temperature fluctuation, you say, okay, that can be addressed by an empirical formula given to me, which is the distribution of classical field configuration. This classical is very important. Classical field configuration, and then you see that you can explain this extremely well, very precisely. Okay, but everything here is the classical field. But the early universe was not a classical object. The energy that we are talking about here in the beginning, everything is quantum. So the fluctuate. Of course, there is a classical space-time, but all the matter and everything is in a highly quantum state. So you have quantum fluctuations before the CMB. So what you want to actually, as a physicist, what we want to describe is we would need a rigorous quantum field theory calculation to show that I can really do this. That I want a underlying to this empirical formula that is supplied to me. I need to derive this from a rigorous quantum field theory calculation and show how this approximation or this assumption is justified, because there is no classical physics in the universe that we are talking. Everything is quantum. Of course, this is very classical, but this is not classical, right? This is, you have to do quantum field theory in curved space. There is no other way. Now, what people do, of course, people have thought about this and they have explained this, and there is a class of physicists think everything is fine. I don't think so, and that is why I'm giving this talk. So let me tell you what people do in the in standard practice. The standard practice is, of course, they use semi-classical picture that you have a gravity which is curved space-time. On the top of that, you have quantum fields. So gravity they treated as geometry, space-time description. Matter field as quantized in the background of a given geometry. And if you are using an inflaton field for the simplest model of one inflaton, so you have the inflaton field which has a very coherent oscillation that is going to drive the classical geometry, but then you have a fluctuation. And that fluctuation you are going to quantize in the background which is given by the coherent oscillation. Similarly, there is a fluctuation in the background geometry, which is the non-perturbative part, which you can think like a for W. But then there is also fluctuation over that, because those fluctuations are the density fluctuations that we are going to see. So these are basically going to give you this metric fluctuation, and that is field fluctuation. And you can show that this fluctuation comes from this. So for that you can use different gauge. There is synchronous gauge, and also you can use Newtonian gauge. And then using Newtonian gauge, you can show that the scalar fluctuation is related with the fluctuation in the gravitational field, which is H0 HIV. So yeah, you can relate these two. So a perturbed field gives you perturbations, and this perturbation is basically when you are at this level, density perturbation. Once you want to calculate the quantum fluctuations here what I'm going to do is that I want to give a quantum origin of the cosmological perturbation, which is classical. So basically, what you do is that you calculate quantum correlations here. Quantum correlation, like the correlation between the field fluctuation
or the metric fluctuation, or the coupling between field and metric fluctuation, and vice versa. So you can calculate all these correlations, and basically these are these objects that you want to calculate. But here everything is is a vacuum expectation value, which is usually taken to be the Bunch-Davies vacuum state. So you need to calculate them and show that after doing the quantum calculation, you are going to get this, which is classical. Otherwise, you don't explain anything. Now, problem is here. So in order to compare with temperature correlations, so for example, this one can be related with temperature correlation. This is the metric fluctuation here. That can be related with the temperature in this direction and the temperature in this direction are correlated. That is giving you an isotope. So this actually can be related with the classical temperature fluctuation. But at this point, this guy is very quantum object. Now, so in order to compare its temperature correlation, the above quantum expectation values are made equal. They are not derived. They are not shown. They are assumed to be equal to a stochastic distribution of classical field configuration. So you forget about all expectation value. Here you make equal to some stochastic classical field. And here we run into various problems. Once you accept this, you are fine. You can do this. But if you ask like how this quantum fluctuation can be given equal to a stochastic distribution of classical field configuration, please explain me. And then you run into problems.
It's doing a Bunch-Davies vacuum.
Yes.
If you some other vacuum.
Yes.
And then also you could
Yes.
any vacuum and that you go to this vacuum is not that important.
Vacuum is important in the more precise sense. Like you need to see the anisotropies and the phenum this exactly to the right quantity amount. Now, if you choose different vacuum, there are two dangers. One, that vacuum may not be Hadamard. Hadamard vacuum gives you a renormalized energy momentum tensor, which is fine. So you need to see that the vacuum has a Hadamard property. Otherwise, and there are not many choices of the vacuum. So except Bunch-Davies vacuum, there is there is not enough. I don't know any other vacuum that can be Hadamard. No. There is a co-moving vacuum, but the problem in co-moving vacuum is that in infinite time you get infinite divergence. Now so there is a paper by Asteker because co-moving vacuum are like instantaneous vacuum states. There is no problem, but if you add them over infinite time, you see divergence. So there is infinite divergences and also ultraviolet divergences. So that is a controversy. But Bunch-Davies vacuum is not controversial. So you basically say that at the beginning of inflation, all the fields were at the vacuum configuration. There was only positive frequency, no, nothing else. You can do this, and that vacuum is very much like mean cross clear because you say that the scale factor goes to constant, and there is basically flat space time and they are so Bunch-Davies vacuum is highly highly not more general. It's a very special vacuum, but that's what people use to calculate this. I'm going to discuss this more. Actually, I'm going to change it with the vacuum that I'm trying to construct. So I don't think that this is a good choice. So the thing is, even before vacuum, whatever you take the vacuum, this is a quantum expectation value, and if this has to be shown that it is actually equal to the distribution of the classical field configuration. So now go to the Weinberg's book, cosmology. I couldn't given the number of pages. Here, these are the things that he says about this miracle that we do. So he says that these are quantum averages. These averages that we have are quantum averages. What is the difference? Because these are not averages over the ensemble of classical field configurations. We see this most clearly in equations that I showed you, which give complex results. So which gives complex results for averages for products of real fields and consequently also depend on the order of the field. So basically this guy, but I have all of them are in general complex number. But you are saying that this is equal to classical field configuration and which is only real. So somehow these quantities which are complex by definition are complex but is completely ignored. And they say it is equal to the real stochastic real field, right? Classical real field. So if it is complex, it changes. If you change the order of this field, it is going to change. The difference between the classical mechanics and quantum mechanics, the wave function lives in a complex. So he says that it is not clear actually how this happens. Just in the so he says that just as in the measurement in a speed, measurement of a spin in a laboratory, if you are using, you are measuring spin in a laboratory, what happens that if you do not do the measurement, you do not know which spins you are going to get. So they said there should be some sort of decoherence here. So there should be some sort of decoherence here which will make this classical. Just in this laboratory spin measurement kind of situation. And this is that the configuration become locked in one of the ensemble of classical configuration with ensemble averages given by the quantum expectation values as in equation that equation. So the thing is there is some kind of decoherence and the decoherence make it classical. And 90% of the physicists working in this believes in that the decoherence is okay. Decoherence make this quantum to classical transition. But there is a problem that he also mentions because it is not apparent how this happens. How does the decoherence happen? Because for the decoherence to happen, these expectation values of the product of real fields must become real. So what he means here, that if this number is this number is a complex number, decoherence cannot happen. It has to be first classical, and then decoherence can give you, the decoherence can kick in. So basically he says that it is not clear exactly how this happens, decoherence. And then he says vaguely, as we shall see, this happens after perturbation leaves the horizon. So you have the initial perturbations and you have the Hubble horizon. So most of the people think that the perturbation cross the Hubble radius and then they become classical. So there are two assumptions here. One is there is something going on like this measurement in the spin of the gravity. And furthermore, there is some kind of decoherence or classical behavior after the Hubble exit. These are two assumptions without proof. So so what I'm going to show that the second one is not applicable. That Weinberg's book says, and the fourth one, which is say that the perturbation goes out of the Hubble horizon and it becomes classical, and I will show that this is not a complete story. So basically, these two way outs are blocked for the following reasons. First, the problem is number one is the symmetry of the initial state, which is intimately related with the measurement problem in quantum mechanics. So what we have, as I say, we have a quantum average, and this quantum average is a complex number, which is this. By force, it is given this. By force, it is chosen to be stochastic average of classical field configuration, and this guy is a real number. So from here to here, it is very complex. From here to here, it becomes a real number. But that is not the only thing. So another thing, somehow this is also anisotropic and inhomogeneous, because this is what we see in the CMB. So not only this is classical, but this is also anisotropic. It should have anisotropies and it should have inhomogeneous. There are classical, inhomogeneous, and anisotropic. All of this is empirical formula. So you need to show how this might happen. Now, the vacuum state that we choose is a Barnes-Davies vacuum, which is invariant under the de Sitter symmetry. And this is a space that is a maximally symmetric space, right? and this is necessarily homogeneous anisotropic. So the Barnes-Davies vacuum is basically invariant under this symmetry group, which is SOD, 1, and it is also homogeneous anisotropic. So the vacuum state, the Barnes-Davies vacuum state, is homogeneous anisotropic. The evolution, so what people do is that say take this at the beginning of the inflation. After the inflation, somehow this is going to give you an isotropic. So how does the isotropic come? It comes dynamically. So in the beginning, you have your Barnes-Davies state, which is in homogeneous and isotropic. So you define this at the initial time. You evolve it from the inflationary stage to the end of the radiation stage, and then you are going to see the anisotropics. Now the problem is, since the initial state is homogeneous and isotropic, and the evolution that in the literature they use is unitary. So if you have a unitary evolution and the state is homogeneous and isotropic, there is no way you can generate inhomogeneity and anisotropic. You can't do that. Whatever you get, it has to be homogeneous and isotropic. But this is not homogeneous and isotropic. We see this already in the CMB, that it is inhomogeneous and isotropic. So how does this happen? There is nothing in your picture, in principle, fundamentally, that can break the symmetry of this initial state. The initial state is homogeneous and isotropic. Take any expectation value, complex or whatever, is going to be homogeneous and isotropic. But we don't see that. So we have a contradiction.
But certainly does not seem to depend on the order in the shoot.
The order is going to change the complex number.
But not the final answer.
The final answer is imposed. You are not. So this final answer should not change. Yes, you are right. But at this point, if you change it, it changes.
But then it is very, very fishy.
It's very fishy. It is empirical.
The order depends. There in one line,
This is fine.
final answer it does not.
So this is a equality, and this one is imposed. This one comes from. This is like imported thing.
So final answer.
So the final answer is that if you have this, there are two problems. One, this is complex. How do you get real? Equivalence cannot kick in until it is real. That's what Weinberg also says. So on the top of that, even if it is become real, you need to say how it is how the anisotropies and inhomogeneities come. There are two problems.
Sujoy,
Yes.
your first line is at 0 temperature.
This one, yes. So this
Second line is at finite temperature.
this one.
Huh?
Yes.
So maybe that is the source. That could be the source of.
That could be the source, but then you need to show that some,
Yeah.
right? Then there is nothing.
But in statistical physics, you do get something like that.
Yes.
In general.
Yes. So in statistical, so the problem in going to the statistical ensemble, I'm going to explain that. There is this ergodic hypothesis that we use in statistical physics is not actually applicable here. We do not have an ensemble of universes. We have just one universe. So it's a single system. You can't even do the other. So the problem here, there are multiple problems. Here I want to say two problems. One, how does this complex value become real? And second, even if it is become real, how do you get an isotropic? Because the starting point that you have, if it is Barnes-Davies state, which is homogeneous and isotropic, and you have a unitary evolution, the final result is going to be homogeneous and isotropic. Now this problem was very heroically attacked by Daniel Sujoy in 2006, this paper. So Alejandro, Hanno, and Daniel wrote this paper, and he attacked that we point out that existing treatment a transition from symmetric quantum state, which is Barnes-Davies, to an essentially classical and non-symmetric state is implicitly assumed, but not specified or analyzed in any detail. So you can't see any quantum calculation. Suddenly it becomes a magic and you have empirical formula, go to computer and do all precision cosmology. So this paper got some attention and basically I'm going to come back to that. That is the problem one that I wanted to say. How do you break the symmetry of the initial state, and how does this the complex number becomes a real number, and that too with the precise in anisotropy in homogeneity. It is not a solved problem. The second problem on the top of that is a quantum to classical transition. So this is a demon. Quantum to classical transition, even in quantum mechanics or wherever you want to say, you are not going to get easy life. It's very difficult to explain. We don't understand quantum to classical transition, to be honest. But here we have to do it. Because we are saying that quantum fluctuation becomes classical, there is no way out. We need to explain it. So what we have, the excuse is this. The excuse is that the mode fluctuation that you have of the inflated field, they behave classically after the Hubble exit. I'm going to explain what it is. And then that is first assumption. There is a second assumption to that. And they remain classical. So basically somehow there is a classical behavior after the field modes go out of the Hubble horizon. But the thing is they go out at the inflationary stage. They have to re-enter in the radiation stage in order to contribute to structure formation. So all the modes that you see here, let me go back to all the modes that you see here in this picture, they went out, they become super Hubble in the inflationary state, and they have to re-enter inside the Hubble radius after the inflation, that is radiation dominant. Then and then, only then they will contribute. So there are two things. One assumption is that somehow the modes, when they go outside of the Hubble radius, they become classical. What classical? What is the definition of classical? Nobody cares. And then they remain to be there even after they enter the Hubble radius. So what exactly I mean is this. So this is, you can see in this paper, we have a very elaborate study on this aspect, 2013. So basically, if you think a toy universe with the inflation rate dx and radiation, after that there is matter, we don't have it here, and then you have a lattice here. Let us focus only on these two, the inflationary stage and radiation dominated stage, because these two are more important for us. Okay? So as you know, you might have known the Hubble radius. This is the co-moving length scale, okay? And this is the scale factor. If you think about the, take A to be the time. So as you go here, the universe becomes older and older because A is function of time. This is the Hubble scale. The Hubble scale, this is a logarithmic plot. The Hubble radius becomes smaller during the inflation. And after the inflation goes to radiation state, the Hubble radius increases. So what happens now? You have three different characteristic length scale. One, which is kind of here. All the modes here, because this is a length scale, you can give a frequency to this, right? So all the frequency of the field modes which correspond to this region, they are always below this. So they are always sub-Hubble. They never cross the Hubble region. If you are here, above this band, so here, if you think about a length scale and you are running time, so this length scale here will go out and become super Hubble, and it will never enter. They will remain super Hubble for life. These are not interesting for structure formation. The interesting thing for structure formation is these modes which are in this band, they exit the Hubble radius, and here they are super Hubble, see, because it is above this line, but they enter because they cross this line. Once they cross this line, they enter in the Hubble region. So the assumption for structure formation is that when they exit the Hubble radius, it becomes classical. And they remain classical when they enter, even in the radiation. These two you need to assume. That's why Weinberg says that the states are locked. It's kind of a log, and you can't change the state anymore. And then with Paddy, we did kind of a thorough analysis, and we say see how this quantum to classical transition happens, right? Of course, there is no best way to do that. So we have this three-stage universe where you start with inflation. After some time, you can fix the time exactly. It goes to T to the power half, which is radiation, and then of course it goes. So this is not required for you. So from inflation, you go to the radiation dominated universe, and these two are like the ratio of the Hubble parameter today and in the inflation. and is like huge disappears, right? So if you take this universe, you can make you can study the emergence of classical behavior. So you take the Friedman-Robertson universe and take just minimally coupled mass scalar field, which is, by the way, are the fluctuations of the equator field. This you can model as a fluctuation of the equator field. And because of the, so you see this is the action, and you do the Fourier decomposition and put it back here, and then you are going to see that the scalar field action is this in the expanding universe, which is kind of harmonic oscillator. So the scalar field action is like an infinite collection of uncoupled harmonic oscillator. Each of the mode function behave like a harmonic oscillator with time-dependent mass. So for example, you can relate this to be the harmonic oscillator with time-dependent mass and time-dependent frequency. And you see that mass is given by the A square, and frequency is here the K square, right? So you can model this as a harmonic oscillator action, and then you can use Schrodinger picture. It's very useful because in that case you can look for a form invariant a Gaussian state to be the solution of that wave functional, and then of course you can put them back in the equation and see that there are two variables, which is n. This should not be alpha, this should be r. So there is n and r. If you solve these two equations, you know the solution of this of this field configuration. This is a long paper. I'm not going to go everything. I'm just focusing on the classical quantum to classical transition. So the way we did it was using linear quasi-probability distribution. They use it, for example, in quantum optics. It's very popular. So is this linear quasi-probability distribution that kind of relates the probability amplitude of the wave function to the probability distribution in the classical phase. So the classical phase space, and you can kind of go to this linear quasi-probability distribution space, and there is a mapping to that. And the proposal there was that you can define a classicality parameter, which is this quantity, and this quantity is giving you the degree of correlation between P and Q, and it is normalized. So if they are highly correlated means very classical. So like a phase space, if you have a phase space, you know Q, you also know P. You know Q and P like point-wise. Given a Q, you kind of have a delta function to P, right? So you know very precisely. So when it is highly classical, this is going to be strongly correlated. And when it is very quantum, there is no correlation. You have no idea where is P and if you know P, you do not have any idea about Q. It's very, very dispersed quantum state. So with that, you can show that this is usually it's a complex quantity, but its modulus goes from -1 to +1. For a pure quantum system, it's completely uncorrelated, and this goes to 0. This is the best way that we can do. Of course, you may not be happy with that, but there is not enough way to kind of quantify classical or quantum behavior. You have to choose one picture. So this is something that is being done even in cosmology, just that they do not have any calculation that we did in this calculation. So with that, you now have a definition of classicality. It goes from 0 to 1. 1 is highly classical, 0 is highly quantum. And you can solve this for.
But this CP is like something what you call in statistics a covariance kind of thing, correlation coefficient.
Yes.
So here you compute these expectations of PQ.
Yes.
So this expectation is computed with respect to the Wigner distribution.
Yes. Yes. That's what you are doing. So this is the way it is in the distribution. You do not take the quantum probability distribution. Take movement. Yes.
Because that does not make any sense.
Which one?
The compute it with the quantum.
No, you can't.
Does not make any
No.
sense.
So for example, this becomes delta function when it is highly classical. So given a P, you know what is the Q. Otherwise, this is very dispersed. So in quantum optics, they do that, and so this is one of the ways that you can do it. Of course, you can come up with your own best choice, but all of the choices that you can take for there are debate, right? Because it's so what we did was calculate this many things we calculated, but here this is the classicality parameter that I'm showing you. So the red is the d theta universe, okay, and the blue is the radiation dominated universe, and the green is the dark energy dominated universe. So we basically solved case by case for different epochs, and we make them continuous and differentiable. Yes.
Yeah.
Yes.
So suppose, as you mentioned, so when CP is close to 1, you are saying that PQ is highly correlated.
Yes.
So it is mimicking the classical
Yes.
behavior. So what would be the opposite value if it goes to -1?
It's also plus or minus. Yes.
No correlation. Zero, no, and it is highly quantum.
Yes. Yes. So what happens if you
See, -1 is anti-correlation.
And
Yes.
-1 is that is why
Yeah.
I'm asking.
yes, it is anti-correlated.
But then why should it be classical? That is means.
Anti-correlated. একটা বাড়লে একটা কম, ওটা বাড়লে এটা বাড়বে।
So it is I would say
That
this.
is correlation.
It's kind of a decoherence that we are talking about. But the problem is it can still decoherent. So this is exactly is going to happen. So when you start here at the beginning of the inflationary universe, so we have the calculation. Okay, so everything is exactly that. You can see this. You start from 0. As you run into the end of the inflation, and then you go kind of sub-Hubble region. So this is the sub-Hubble case, correct? And this is the super-Hubble case, and this is the intermediate case. The intermediate one are the most important for structure formation. Super Hubble, they exist and we never see them again. So you can neglect this. But still you can see that for the Super Hubble modes, it starts from 0 and it goes to -1 and it stays -1 forever. So it is true that when the modes become Super Hubble, they remain classical. It is true, according to our analysis. Because it is like -1. You see that they become Super Hubble and then so the Super Hubble modes by the end of the inflation become -1 and they do not change after, even if the universe changes. So they are stick to -1. But the problem is these are not the modes that are going to give the structure formation. These are these guys. And what happens to these guys that these modes, when they go out by the end of the inflation, they are going to be really classical. But as they enter in the radiation dominated universe, suddenly it started oscillating. So basically, what I'm trying to say is these guys, which give me the structure formation, when they exit the Hubble radius, they are very C is like -1. But when they enter, suddenly C becomes complex and it starts oscillating. Here, these are the oscillating behavior. So it does not. So you cannot lock the state. That's what is important for structure formation. So it kind of goes to very classical, but as they enter, the Wigner distribution function tells you that it is very quantum object. So there is a quantum fluctuation. Those are quantum fluctuations. Those are not particle creation. We actually calculated particle creation and we showed those are not real particles. Those are virtual particles. So basically what happens at this time in the radiation dominated universe or at the end of radiation dominated universe is highly oscillating, it never settles down. It becomes very large for realistic value, which is 10 to the power -55. Here we have like 0.0001, but cosmological value is 10 to the power -55. So basically this oscillation stays for long and long time. It never changes. So basically you cannot lock it. So the reason I say now, if you see Weinsberg book, Weinsberg says maybe this happens, right? Maybe this quantum to classical transition happens after the perturbation leave the horizon. But what I'm trying to say, this is not the complete story because they can leave the horizon, but they have to enter again in the radiation stage before giving structure formation. And when they enter, they become highly classical. So this is not a complete story. It is a half story. You need to analyze what happens when they enter in the whole area and everything breaks down. So this is like 10 years ago that I studied and stayed with me still today, and that's why I'm doing this kind of work. So basically, the spin measurement that the equals like the early universe is like a spin measurement. It is outright crazy because who is doing the measurement? In the laboratory, the spin measurement there is an observer. In the early universe, if you think about that, I'm breaking the symmetry of the Banzevi state by measurement. Who is doing measurement? Right? So there is this problem of this is where the measurement problem comes, and this is not acceptable. This is not a complete story. So that means that the quantum origin of classical cosmological density perturbation is a wide open problem, and it touches foundational aspects of quantum theory. So you cannot get rid of easily. For a resolution of the aforementioned problem, there is some, of course, work, and people are not sitting idle. The idea is, what if you can dynamically break the symmetry of the boundary state? So this is in the beginning of inflation. So what if I change, but dynamically make this state to some psi, and I calculate this after inflation in the radiation era, and I generate an isotropy in homogeneity, because this state will break the symmetry of this state, right? So what if I do this dynamically? Now, you can start with the Barnes-Davies vacuum, which is homogeneous and isotropic, and break the symmetry and go to some inhomogeneous and anisotropic vacuum state and calculate this. You still cannot explain quantum to classical transition. At least you are going to get inhomogeneous and anisotropic. So, how do you do that? The problem I already mentioned, there is no unitary transformation that can do it. And that's why people went into non-unitary evolution of quantum state, which is given by dynamical objective Colas module interpretation of quantum theory. I do not, this is another talk to explain, but these models are getting very popular today. There's a huge experiment going on to verify objective Colas theory. The reason is this: quantum foundation, people are not happy with the foundation of quantum mechanics, and there are two types of alternatives people have suggested. One is, for example, manual interpretation, Bohmian mechanics. Those theory and quantum mechanics have exactly same prediction. So those are like interpretational change, but they have the exactly same prediction as quantum mechanics. The only theory, only foundational quantum mechanical theory that differs from quantum mechanical prediction in certain cases is the dynamical objective Colas model. And it says that the fundamental evolution of any state has a unitary part and also has a reduction part. Just that this reduction is very small, so most of the cases you have a unitary, but once you do measurement, this part will dominate over this. But in general, they both exist. Okay, this is the ontology of the theory. Now, according to this theory, there is always associated to the unitary evolution, there is always reduction. So this is also Penrose's hypothesis that Penrose has this can come from gravitational, influence collapse. Because classical or quantum, you cannot shield gravity. So gravity may give some noise which have this is Penrose's hypothesis, but not study. But this is the fundamental evolution, and of course, now you go to this what kind of theory, which usually you do not take, and say, okay, maybe we can go to this, this continuous spontaneous localization of wave function, because this theory can break the symmetry of the initial state dynamically without an observer. So this paper has a calculation of generation with Daniel and these people. Philippal is one of the foundational person to do this particular model. So there is a nice calculation to this, but this calculation has drawback. Okay, I'm not telling what is the drawback, but as a first attempt, this is very nice because this is the only paper where they calculate all quantum mechanics. There is no classical empirical formula. Everything is done quantum mechanically, shown to be giving the classical empirical formula, which was lacking, right? Of course, while doing this, there are some problems, which is why I'm still continuing with that. And you can go, I mean, this is not dated. So there are many papers, not only that, you can see many papers who have contributed to this. They are using this objective collapse theory. Sometimes they say dimensional reduction theory. So all these things, paper have different uh, calculations to explain this symmetry breaking and emergence of anisotropies by a spontaneous collapse of this thing. Okay. Now, why I am still working on that? The problem remaining that in those calculations, there is no physically motivated quantum state that they can choose. They choose some state, and those states mostly are not Hadamard state. So if the state is not Hadamard, your semi-classical gravity is ill-defined. Your Cauchy problem cannot be defined. So you get rid of one problem, you fall in another problem. So those states that they choose are legally unacceptable. Of course, they can show that those states can give this thing, but if you take them and see the Hadamard property and they use the not Hadamard. Now that is a problem. So we need to choose a state which is homogeneous and isotropic, but that does not have that problem. So why it is important to locate a state in the early universe? So it is a philosophical, but if you can pinpoint the quantum state of the universe, the early universe, post-inflation, then we can understand much more about the early universe. If you can pin down the state after the inflation, we can do many things. For example, you can look for primordial gravitational wave coming from these, right? And you can there are many things that you can do. You can build a cosmological perturbation theory based on this state. Everything that they have done for Bunch state, you can do it with your state. So, now, also, it is important to know the state because a Hadamard state is necessary for well-defined semi-classical gravity framework. Semi-classical gravity means that G mu is expectation value of T mu is zero normalized. Unlike the Einstein equation, which is second order, this is fourth order differential equation. And because it is a fourth order differential equation, the initial value formulation is highly non-trivial. And it becomes and it is proven that I have also written one paper that the initial value problem is well defined in cosmology if the state is Hadamard, if the psi is Hadamard. Now we need to find this state. Otherwise, we need to find a Hadamard state. Otherwise, the semi-classical gravity formulation is crazy. It has runaway solutions. You cannot trust it. So the new task that I have been working for many years now, very slowly, is that construct a manifestly inhomogeneous and anisotropic quantum state in the radiation dominated era, because I need it in the radiation dominated, which is Hadamard and can be physically well motivated. Okay, so why it is important? Because well, if you know Hadamard and inhomogeneous and anisotropic state, that can be the state after you break the symmetry of the Bunch state. Okay. How do you break the symmetry? Okay, maybe collapse. I don't know. Okay. No, so this part, which is my work, is basically the recipe to construct this vacuum state that I have defined to be T vacuum state. This is the name that I have given. That T vacuum state. Okay. So yeah. Sorry. So so I'm just going to go through the recipe. It may be boring or whatever. I can discuss later on. So I started first paper I wrote in 2018 about this. So what I show this result was with me for about 4 years. I could not understand. So I did not write anything until 2018. So what happens is that if you start with a FW metric, which you know, okay. So again, this is a recipe, right? In the recipe, I have three sides. One is the geometric side. Another, I will come two more sides, and finally I have a field theory side, right? Because it is that one. Let's talk about the geometric side first. Because in quantum field theory of space-time, geometry and the quantum field part goes hand in hand. The isometry of the space-time is so important to construct the quantum field theory, right? So geometry-wise, you start with the FW universe, and if you do this kind of transformation, which is a conformal diode transformation, okay. Right now I do not know what is M, and also you can choose A to the A is like e to the power n. and I want to do this for all of type of transformation. Okay, this is for u greater than 0 and this is for u less than 0. And I go, if you do this, the metric FRW metric goes to this metric, which looks ugly. It becomes this where A and B looks really ugly, where you have M and N. N comes from this, right? For radiation dominated because N is half, right? For matter dominated N is 2/3. So you have M and N, and you get kind of a ugly looking. But what happens if you choose M equal to 2 and N equal to half? That means for the radiation stage, A and B becomes this. Still, you don't feel worried as exactly is this, right? So I mean, let me just do this. You can fix the lambda, which is there is a way to fix it. 1/HE, H is the Hubble parameter of the inflationary state, and you can introduce new time and space coordinate, which is related to your transformation v and u coordinate, right? So you do that, and suddenly you get this. So you started with the homogeneous and isotropic FRW, and you get a spherical symmetric FRW. You reduce the symmetry. Okay, so the space-time becomes this, and this is for the sub-Hubble region, and this is a super-Hubble region. It kind of looks like black hole, but it is not. For Schwarzschild black hole, this is multiplied with d square and divided by d square, right? Here it is both divided. It's not a black hole. Although it looks like very much, the complexity is hidden here in H, because H is the Hubble parameter as a function of T and R. So this metric is inhomogeneous and anisotropic, because H is a function of T and R. So kind of, I went from a homogeneous and isotropic metric, and you can do a transformation, and you come to a metric which is spherically symmetric, but it is manifestly inhomogeneous and anisotropic. Okay, so you break the symmetry, right, of the space time. So in the geometric side, what I want to do is that I want to construct a field theory in these coordinates. In the coordinates which are inhomogeneous and anisotropic. Why? Because my goal is to kind of define a vacuum state with respect to these coordinates. Because these coordinates are inhomogeneous and anisotropic, and if I can find a quantized field and define a vacuum state which is isometric under this, then I have an inhomogeneous and anisotropic vacuum. Whether the universe was in that state, I don't know, but you can construct. Okay, that is the goal that I want to do. I want to go away from the homogeneous and isotropic spacetime. I want to go away to some inhomogeneous and anisotropic spacetime, and I want to construct a quantum field theory where the vacuum state does not have homogeneity and anisotropic. Then the question is whether that vacuum state is Hadamard, whether that vacuum state can be well defined. There are many conditions on that, right? Whether I can even quantize the field in this space, because H here is a function of T. Now, for the construction of quantum theory, I need to do a foliation of the spacetime in the new metric, and let me just go through. So here I have a foliation. This is a mathematical plot. So here you have a P and R coordinates, and this is a constant eta. Eta is the cosmological time, right? dT/AT. So cosmological time slice looks like this in my coordinate here. But the cosmological slice, the full space-time is foliated. Okay? So eta equal to, so here for example, I can foliate t equal to constant like this, right? Straight line. And then r equal to constant like this, right? And I can say, okay, I can define my initial state at t equal to, let's say, 1. And then I'm going to evolve with the initial state from t equal to 1 to t equal to 2 to t equal to 3, and I can have a well-defined quantum field evolution of the state. But what I need to show that this foliation is complete. In order to show that, I need to show that the complete eta equal to constant slice can be inside this metric. Otherwise, this foliation is not complete. So in order to complete the foliation, here you can show that it is possible to have a sub-Hubble region and super-Hubble region joined here at a Hubble radius. There is like a time slice eta equal to constant, Also, you can have a small r equal to constant, which will look like this in my new coordinate, so that the full space-time foliation, this is like a Unruh case. Think about Unruh foliation. So where you have a Minkowski space and time, and you have Unruh time and space, right? So it's like that, except that this is not Unruh. So you have this P and R frame, which is what I want to quantize my field. And in that frame, you can visualize your cosmological foliation like this. They are deformed, but nevertheless they are complete. So what I know that the quasi problem is well defined because I can have the full foliation of the space. Okay. Then the second part is that these T and R observers, who are they? So this I just did a mathematical transformation here, and I go to some mathematical manipulation, and I go to this metric, right? But who are they? Who are those guys, right? Are they? Can I identify these observers who has T as time and who sees the radiation dominated universe as a spherical symmetric homogeneous system? So I kind of want to identify these observers, and that was another paper that I wrote, and I want to skip the calculation here. But what you can show that 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 the if you start with a static de Sitter metric, static de Sitter observers are well known. So static de Sitter observer looks the universe like that. That is the static de Sitter metric, which is like a black hole, right? These T and R, when these static observers living in the de Sitter state, see the space time like that. But when the universe makes a transition from the de Sitter to radiation, the metric changes like this. So static observer living in the de Sitter phase have this metric. But when the universe changes and go to the radiation boundary universe, this is the metric. And this is basically the metric that I am being using. Just a rescaling of this time. This is E. So you can rescale e to the power 2ht times dt times E times 2. And that metric is going to be the metric that I got before. Here. This metric. So basically now I have a cosmic identity of this observer. These observers are the de Sitter observer in the static de Sitter, but they do not live in the static de Sitter phase anymore. The universe has a major transition, and they are fall from the de Sitter stage to the radiation state, and the metric becomes this. So now that I know the cosmic identity, then if I say that there is a vacuum corresponding to this time, then I will know vacuum for whom. Okay. But this metric is again inhomogeneous and anisotropic. So the last part, sorry, 2 minutes. So the last part is basically to do the field theory calculation. And here again I do first the 1 plus 1 dimension, 3 plus 1 dimension is going on. So you start with this metric. Right now I am taking 1 plus 1. And of course you have a conformal time cosmological space time, and this is the new metric in the TR coordinate that I have defined. And you can in 1 plus 1 dimension you can expand the field, which will look like this in the cosmological frame, and will look like this in the new TR frame. And here you can define a cosmological vacuum state, and here you can define the T vacuum state. Okay, so this is the vacuum state that is my input, because this vacuum is manifestly homogeneous and anisotropic. You can define this easily into, and then you can calculate the Bogoliubov transformation, Bogoliubov coefficients. So basically, you are saying I have a cosmological observer, and cosmological observer is looking at that vacuum state, and they are finding some particles, and that is the particle number density that you can calculate. Okay? So you have this is not a black body distribution. The expression is in the paper. You can see this that there is the number of so this number of particles being created by from the vacuum, and they are being looked upon by the cosmological observer who are the physical observer. So in the physical observer, now the most important thing is not the particle number, but the renormalized energy momentum tensor, because will tell me whether that state is Hadamard or not. So I can calculate. I calculated this in two dimensions. It's not a big problem. You can do this using Unruh's Fooling calculation. And this is the PUU, PVV, and PUV in the T vacuum state. Now, first of all, you can see that U goes from minus infinity to 0 and 0 to infinity. So whatever value you choose for U and V, they are always finite. So for entire range of U and for entire range of V, there is no divergences in the zero energy momentum fields. So that means that T vacuum is Hadamard, at least in 1 plus 1 dimension, because they are not diverging at anywhere in the space. That is the essential and sufficient requirement for a state to be Hadamard. So I know that now in 1 plus 1 dimension T vacuum is a Hadamard state. And then because it is a tensorial expression, you can make the transformation from the cosmological frame to the co-moving frame. So the co-moving frame are like our nearest, the co-moving frame is like we. So you can calculate the co-moving frame expectation value in the co-moving frame in the T vacuum state, and you will find this expression. So you will get energy density, you will get a negative pressure, and you get a momentum density. Okay, so these things will give you radiation, they will give you energy as an astronomer. If the universe was in T vacuum state, you are going to see this. So of course they are diluted and all that, but this is the energy density, this is the pressure, this is the momentum density, and that you see is interesting that this is negative pressure. So there is an anti-gravity effect. There's a repulsive gravity effect coming from this because this is negative. You can see that they are consistent because you can calculate the trace anomaly and it is going to be 0. So this is radiation level. So you can kind of cross-check them; they are correct. What is important here, I just want one line, is that this radiation from T vacuum state is inhomogeneous and anisotropic. Can anybody answer why? Why these are inhomogeneous and anisotropic? These results. Anybody? From students? Exactly. It depends on R, for example. It cannot depend on R if it is homogeneous and isotropic. So this recalculation that is coming out naturally gives me a result which is inhomogeneous and anisotropic. Why? Because this vacuum is inhomogeneous and anisotropic. So T vacuum, by definition, is inhomogeneous and anisotropic. So you get inhomogeneous and anisotropy free. You don't have to break any symmetry of blocks, right? So you get this. Of course, now the thing is that whether this is the anisotropy in CSE, I have maybe 5 years research more. But what is the main message is this. The main message is this, that the lack of homogeneity and anisotropy in the CMB map might be signaling to an initial quantum state of the universe which is manifestly inhomogeneous and anisotropy. So if you believe this is coming from a quantum state, maybe that quantum state is itself inhomogeneous and anisotropy, and we do not have any candidate for that. Forget about here. There is zero candidate for an inhomogeneous and anisotropic state which is other. Okay, so T vacuum is built, is kind of engineeringly built in order to serve this purpose, and so far this is the only candidate. There is no other candidate which lacks homogeneity and anisotropy. Okay, so that is the main message that I wanted to say. Conclusions: we have discussed open issues related with quantum generation of classical density perturbations. We motivated kind of necessity of a well-defined quantum vacuum state, which is homogeneous and anisotropic. And then we said, okay, since no such quantum vacuum ever existed in the literature, we made extensive effort to do so in a systematic manner. We showed if the state of the quantum matter field after inflation is T vacuum, we naturally get energy density, pressure, momentum density, all lacking homogeneity and anisotropy. Of course, we have not showed that this is the anisotropy in this case, right? But theoretically, we get that. We further show that T vacuum is Hadamard in 1 plus 1 dimension. It is finite everywhere in the space. So, although T vacuum is motivated here as a final state after collapse, this is how I motivated it, but this is not essential. because there are cosmological models even without inflation. So there are, not all cosmological models has inflation. My T vacuum state exists is the radiation dominated. It does not need inflation. Of course, it may be the state after collapse. So T vacuum state can have its own life, even if there is no inflation. Right? So one can further ask physical consequence of this vacuum, such as primordial gravitational waves and everything. So for example, if you see a primordial gravitational wave, which are gravitons, but they are anisotropic, you cannot explain it in any other vacuum. You need to have a anisotropic vacuum. Then further research is necessary to generalize the field theoretic calculation to 3+1 dimensional setup, and probably few weeks we are going to finish the paper about 3+1. So that's all. Thank you.
Very nice talk.
This vacuum looks quite similar to the Unruh vacuum in the black hole.
So Unruh vacuum is very, so for example, is very good question. So in the black hole spectrum, we have three different vacuums. One is the Bullwire vacuum, one is the Unruh vacuum, and another is the Hartle-Hawking vacuum. So Hartle-Hawking vacuum, for example, is a toy. It's like a black hole exists for infinity, from past infinity to future infinity. In that case, you can define Hartle-Hawking vacuum, right? Also, there is Bullwire vacuum, but Bullwire vacuum is only defined outside the horizon. So it diverges at the horizon. So that is a ill vacuum state at the horizon, but it can still define a compact object without horizon. Still define. Then there is this Unruh vacuum, which is global vacuum. Like if you have an observer from outside and you are falling into the black hole, all the way Unruh vacuum is going to be very. And this is similar because this T vacuum state is a global vacuum. It is not a sub-Hubble vacuum state or super-Hubble vacuum state. It is a global vacuum state for all of them. So in that sense, it is similar to Unruh.
What are your transformations for BAE?
Okay. Yes.
Yeah, so you choose some specific values of m and lambda here, right?
Yeah, in beginning I just put a m and
Yeah, but then in the next slide you choose
yes,
some specific
yes,
values.
yes.
So why do you choose these values? One and two?
So for example, m is not so important. M is kind of whatever you. I wanted a space-time with symmetry. Okay, so you can, if you do not have any symmetry, you cannot construct quantum field theory. Okay, so m is can be any number, right? If m equal to 1, then this is a linear transformation. There is nothing. It is no transformation at all, right? So at least m should start from 2. Then it is a non-linear transformation, and it is not a Lorentz transformation. Lorentz transformation is linear. X equal to x minus bt by blah, whatever. So it is a linear transformation. So here, m has to be more than 1 in order to have a non-linear transformation, so that you can construct a field theory which is unitarily inequivalent. Otherwise, if you have flat space-time Lorentz invariant field theory is unitarily equivalent in all fields, right?
So vacuum that you're constructing depends on the value of m.
So when you have this value of n, for example, you get nice symmetry. N is important. For example, n is much more important because n gives you a0 to t to the power half. And t to the power half is basically telling you that in the radiation dominated universe, if you have m equal to 2, then you get this space.
What I'm trying to say is like, so by choosing a specific value of m, you construct one kind of a vacuum, right? That you want.
No, first you construct a space time which has some symmetry.
Right.
Okay. So what was interesting to me, I get a spherical symmetric space time, which is inhomogeneous and anisotropic, and it is very much like, uh, you can do one of field theory on that.
So you get the spherical symmetric this space time.
Yes.
Take it for n is equal to 2.
Yes.
So had you taken some other value, say for example n is equal to
Huh.
3,
You will not get.
then you will not get this spherical symmetry.
No. So here you have some T and R.
There is a catch behind it, that basically it's a Jacobi's or Boolean or not, it's a classical thing, it's a conformal transformation, well-defined conformal. That's the way it works to M is equal to 2. Otherwise, other things will not work.
Will not work.
No.
But the important thing is it works for m equal to 2 for n equal to half.
Yes.
So it could have been n equal to 1 over 5. Then it is not important to us because it is neither radiation nor matter. So it is not a. So n is very big, right? You know that cosmology. So this n value cannot. N is like infinity for inflation, right? Half for radiation, 2 over 3 for matter.
So for example, have you taken n is equal to 2 over 3
Yeah.
for matter?
Yeah.
Then is there any value of n for which you will get a spherical
No.
symmetry? You will not get. So this is very special for radiation and the combination of that.
Yes. Yeah. But I wanted in radiations because because at the end of radiation you have those anisotropies, right? So fortunately it worked. So it was like I got it like an accident, right? And then I didn't know what to do it with that for many years because it looked artificial for me to do anything with that. It looks like a accident. But then it took many years. As I told you, I've been thinking this for about 10 years now. So it took many years to actually put this in context, like how this accident, mathematical accident, kind of is important, right? Can be important. So the way I am telling you that it may be important because I get a inhomogeneous and an isotropic spacetime, and I can define a vacuum state which is isometric under this symmetry. And if the universe was in this vacuum state, then we, as a co-moving observer, will get an isotropic. That's what we see in CME, right? Without.
Okay, so we can have some discussion in the tea time. So there are back-to-back talks. At 4 o'clock there is another talk. So there will be a. So let's thank you guys for a very nice talk. Let's have tea now.
Yes. Only the big